Welcome to new lecture on stiffness metrics method. And today we are going to discuss about displacement transformation metrics represented by the symbol A. So we have already studied about what is flexibility metrics method, in which we discussed about force transformation metrics. Similarly, in stiffness metrics we are discussing about displacement transformation metrics. So it is a matrix which connects a system displacement with the element displacement. So we know there is system approach and element approach. We are converting a system into small elements. That's why system will have a displacement represented by the small letter r, and element will have displacement represented by the small letter q. So displacement transformation matrix connects the system displacement with element displacement. So a quick recap of what is force transformation matrix. It is a matrix which connects system force with the element force. Okay, so coming back, displacement transformation matrix may be represented as small letter q is equal to a into r, where a is the displacement transformation matrix. So let's see how we can find the value of displacement matrices. Okay, example 1, let's consider a beam ABC, continuous beam, two ends fixed, and the joint B is a roller support. So the degrees of freedom here is 1. Degrees of freedom is 1. At the joint B, there is a rotation possible, and also at the joint B, you can move in x direction. But since no horizontal loads, we are neglecting that one. Hence, the degrees of freedom is 1. So, hence, the degrees of freedom is 1. The system coordinate is also 1. Okay. So, we define the system coordinate as R1. Now, element coordinates, each element will have two rotations or moments that is being represented here. It may be represented as 1 dash, 2 dash, 3 dash, and 4 dash. Then displacement transformation matrix. How will you derive it? You are applying, the first step is that you apply unit displacement at system coordinate 1. So this is my system coordinate 1. So I apply a system unit displacement and find the corresponding element displacement values. We have 4 element nodes, that is 1 dash, 2 dash, 3 dash, 4 dash are the 4 element nodes, and only one system coordinate, that is R1. So by applying a unit displacement at R1, I find the value of 1 dash, 2 dash, 3 dash, 4 dash. Okay. So basically the meaning is that displacement transformation matrix is nothing but the value of displacement of the elements. It is nothing but a element displacement value when we apply a unit system displacement. That is, when we apply R1 equal to 1 or unity, the corresponding element displacement value is called as displacement transformation matrix. So it is nothing but displacement value itself. So when I apply a rotation, unit rotation at point B, that is at point B, the theta, that is slope value will be 1. And the far end A and far end C are fixed, hence slope value is 0. Hence, just adding up the values A11, A21, A31, A41. A11 represents displacement at 1 due to load at 1. A21 represents displacement at 2 due to load or displacement at 1. Okay, A31 displacement at 3 or displacement at third element coordinate due to unit displacement at first system coordinate. Okay, A41 is equal to displacement at a fourth element coordinate due to unit displacement at first system coordinate. It is 0, 1, 1, and 0. This is 0, 1, 1, and 0. And going to another example, and consider a continuous beam. At a joint B and joint C, there is degrees of freedom. Rotation is possible. Hence, we defined the system coordinate as R1 and R2. And element coordinate 1 dash, 2 dash, 3 dash, 4 dash. That is beam elements. We assumed it as rotation at the two nodes. Now, defining displacement transformation matrix, apply unit rotation at the first point. That is as in similar to previous example. But the idea is that you have to keep all other joints, keep all other joints fixed. That's why at the joint C, I applied a fixity. Hence, at joint B, you have unit rotation, that is theta equal to 1, theta equal to 1. And at joint A, you have theta equal to 0. And at joint C, you have theta equal to 0. Now, that is written in the first column of the A matrix, that is 0, 1, 1, and 0. Now, apply unit rotation second system coordinate R2 equal to 1. That is at this point, but are keeping all other joints fixed. Joint A as well as joint B is fixed. That's why at joint B theta is equal to 0. Only at joint C there is a theta equal to 1. Hence the displacement transformation matrix becomes 0, 0, 0, 1. Now example 3. Here there is a difference in the moment of inertia values. Hence, two system coordinates are considered. That means at the point B, there is a change or increase in moment of inertia value. So at that node, we should consider two system coordinates. One is translation and other is rotation. Hence, R1 and R2 are considered as system coordinates. Now, finding the element coordinates and then applying the displacement transformation matrix. So first one, apply unit displacement in first system coordinate. First system coordinate is a concentrated force acting downwards. It will result in what sort of a displacement? It will result in a downward motion, right? That is delta equal to 1. A translatory motion, a delta equal to 1 is a displacement produced, and hence a deformed shape is shown in the yellow color. And look at the joint A and B. There is a small angle or a slope value produced, that is called alpha 1 and alpha 2. We have to find these alpha 1 and alpha 2 values. Okay. Even though the fixed end A is fixed and end C is fixed, there is a slope. Since we have pushed it downwards or a translation occurred, there will be a slope. Okay. So tan alpha 1 is equal to opposite by adjacent. That is, opposite length is, this is tan alpha, so opposite is this one, opposite by adjacent length. Okay, that is delta by L1. Delta value is 1, hence 1 by L1 is my alpha 1 value. Tan alpha is taken as alpha itself because alpha value is very small. Similarly, tan alpha 2 is equal to alpha 2 equal to delta by L2. That is 1 by L2. Now add the matrix values, that is the displacement transformation value. Look at the sign. It is anti-clockwise. Hence, we have to give the value as minus. Okay. And look at this one, alpha 1. It is also anti-clockwise. Hence, minus L1 because our system coordinate is in clockwise direction. Okay. How we will mark the alpha 1 angle? Since the system moves downwards, an equal and opposite rotation is induced in the fixed end, and hence it is acting in anti-clockwise direction. Or you can simply measure it from the displaced shape to the undeformed line of action. So this will act in this direction. From this point, it will act downwards. Okay. Similar way here, it is clockwise. Here also it is clockwise. So alpha 2 is clockwise and alpha 1 is anti-clockwise. So alpha 2 is 1 by L2, that is positive value. Two positive values. Okay. Now first case is over. Now apply second case that we have studied already. Applying unit displacement at node 2 or in the direction of second system coordinate, theta 1 equal to 1, theta 1 equal to 1. At the two end, it will be 0, that is 0, 1, 1, 0, and hence we get the A matrix. This is how we calculate the displacement transformation matrix. Thank you.